Hello, everybody. I hope you're doing well, and I hope you're studying your calculus hard. All right, so this is a short video. I hope it's going to be a short video to go over the problems of your practice test number 3. Practice test 3, of course, is on chapter 4. And even though the last section, 4.8, is optional, you can use that method by Lagrange called the Lagrange multipliers if you would like to use in optimization problems. Okay, so my intention is to go over all those problems in the practice test, and the answer key is already provided. And so let's get to it. Practice test number 3. Okay, so as you know, this is what the practice test looks like, and it covers these 4.1, the sections 4.1 to 4.7. All right, and again, there is an optional section 4.8 whose method you can use if you like. And it looks kind of short, it's only 1 page, but if you look at the last few problems, and you may have tried these before, the last few problems may take a while. All right, and so this is a comprehensive sort of a practice test. And if you do these questions, I am certain that you can do well on the actual test that you will be taking on chapter 4. Okay, so an answer key is already provided for you. Let's go over these fairly quickly. Okay, number 1 was about this problem, right? Here, let me just use red here. The function given is the natural log, or ln, of y minus x squared. All right, what's the domain? Well, the domain, the domain is the natural domain, which means at every point xy at which this makes sense. And by the way, at this point, you should not be saying anymore that the domain is a set of all real numbers. Okay, remember, because we have an extra dimension now, whatever the answer is, the domain will be a subset of not the real numbers, but the plane. Okay, and plane is, of course, a set of all ordered pairs x, y. And in this case, you have to pick a particular subset of that. So what is the domain in this case? Well, because the natural log only takes the positive arguments, right? You have to make sure that y minus x squared is positive, not even 0. Okay, it has to be positive. So simply meaning y is greater than x squared. And so y is equal to x squared, of course, is the parabola. And so if y is greater, then that would be all the points inside the parabola. All right. Now you could technically say the domain is a set of all x, y. You don't have to write it in this precise way, but it's a set of all x, y such that y is greater than x squared. This is also an acceptable answer. I mean, it is the more precise way of doing this. But since you are asked to sketch the domain, you would have to have a picture like this showing the parabola. And the reason the parabola is in a dotted line is because all the points, or none of the points in the parabola are actually in the domain. All right, number 2, the part B, describe the level curves. And when I just say the level curves, just sketch like a few, maybe 2 or 3, probably 3 would be a good number. And so you set the function equal to k being some constant, okay? And then, of course, this means in terms of the exponential function and using the number e, this statement, which is a complete sentence, is equivalent to saying e to the k is equal to this argument, right? So e to the k plus x squared is your y. So of course you solve this for y because that's how we graph things, functions on the plane. So y is e to the k plus x squared. Now, if this part is 0, of course that is y is equal to x squared. And when is this equal to 0? Well, e to the 0th, remember, is not 0. So in order for this to be equal to 0, well, you can't, okay? You can't set this equal to 0. So if, just suppose k is equal to 0, okay? In that case, you have y is equal to x squared plus 1, all right? And as k goes negative and negative and negative, 2, -3, -4. This does approach 0, but it never gets to 0. It's one of those fundamental ideas of calculus or mathematical analysis that e to any number is non-zero. Okay, and it turns out even if k is a complex number, e to that number can never be equal to 0. Okay, but anyway, e to the k is always a positive number, and as k goes down to to negative infinity, this point gets closer and closer to the origin, but it never gets to the origin. Now, as k gets bigger, if k is equal to 1, for instance, right? So this equation is y is equal to x squared plus e to the first, which is e. And e, as you know, is about 2.7. And so this is the graph. And so once you draw like 3 or 4 of these, you get to see that this is a family of parabolas, right? The level curves are a family of parabolas. Of course, it's symmetric with respect to the y-axis. All right, part C, evaluate the gradient at 1, 2. All right, so what do you mean by gradient? Of course, you know the gradient is this two-dimensional vector consisting of fx and fy. So you evaluate fx, and here's the equation. And so using the chain rule, you know y minus x squared becomes the denominator. And then the numerator, with respect to x, you get -2x. And with respect to y, you just get 1. All right, and so then right, this is what you get. And then you evaluate them at, 1 and 2, and you get the gradient to be -2, comma, 1. All right, and so that is your gradient. And you are to draw this at the point 1, 2. And so you can see I have done that right here, right? This is the point 1, 2. And what you are to do is to draw this curve, which is -2 and 1. So, it'll be in this direction. And that's what I drew here in blue. Okay, so the blue vector drawing here is the gradient at the point 1, 2. And notice here, of course, it is perpendicular to the level curve where k is equal to 0, right? This is perpendicular as we expect, because that's one of those properties of the gradient vector. All right, and then finally, part D, what is the maximum rate of change at 1, 2? And remember, the maximum rate of change is the magnitude of that gradient. So all you have to do is to find out how long this is, and of course the length is the square root of 5, right? And so by this time, I hope you can state something like this at this point, at the point 1, 2, okay? The direction in which you get the maximum rate of change is the direction shown by the gradient, which is -2, 1. And that maximum rate of change at this point is the length of that gradient vector, which is the square root of 5. All right, so those are good things to remember. All right, number 2, G is this function. All right, and we are to answer each of the following questions. Part A, what is the domain in your own words? Okay, so here is, this is what we call a rational function, right? You have a polynomial over a polynomial. And because you don't want to, you want to avoid the 0 denominator, what you do not want is y squared to be equal to x squared, right? So you want to avoid that. And so these are the points that you need to avoid. And so don't say that the domain is this, okay? It's quite the opposite. The domain is every point but these points, right? And of course, these are 2 lines, okay? And you see these 2 lines right here in red. So the domain is every point off of these lines. In other words, the domain is a set, and here's a precise way of writing this, right? The domain is a set of all points x, y such that x is, y is not plus or minus x. In your own word, you would say the domain is the set of all the points not on either of these 2 red lines, okay? So that's a way to say that. Part B, show that this function does not have a limit at the origin. All right, so how do you show that the limit or a limit does not exist at a particular point? One way, and probably the only way we know how in this section, is to show two paths along which you get different limit values, right? Because remember, if the limit does or did exist, then that limit number has to be the limit regardless of how you approach this point 0, 0. And a typical, things to try, the paths or approaches to try is these ones, number 1 and number 2. Notice here, along path number 1, x is always equal to 0, right? And y is approaching 0, but we don't let y to be exactly equal to 0. And so as long as x is equal to 0, this expression just becomes 0, right? Now, it is defined because we make sure that y doesn't get exactly equal to 0. Y is a small number, but never is equal to 0 along this path. And so that means this is always 0. Okay, so in other words, as you approach the origin along path number 1, the function is constantly 0. Now along 2, notice here, y is constantly 0, but x is not. X is approaching 0, but x never is 0. So in this expression, y squared goes away, and basically this is exactly 3 at every single point on 2. And so as you approach the origin from this direction, the value of the function is constantly 3. So 0, 0, 0 all the way here, 3, 3, 3 all the way here. Right? And so the fact that you get different answers here shows that the limit does not exist at the origin. You have had several problems in your homework like this. Okay, part C. Where is the function continuous, right? So how do you know when the function is continuous? And by the way, I think I emphasized this, but continuity turns out to be one of those extremely, extremely important concepts in advanced mathematics. All right, so you want to make sure you understand if you are, planning to take more mathematics courses in four-year universities, you really do need to know about continuity. And so when is a rational function continuous? On Tuesdays and Thursdays only? No. Okay, it's always continuous. But there is, of course, a little disclaimer. The function can't be continuous if it's not defined, right? And for rational functions, okay, for instance, in algebra, you learn that every polynomial is continuous everywhere, at every real number, okay? And when you have x and y, if you have a polynomial function in x and y, it's always continuous everywhere for every x and y. But in rational functions, okay, we have a theorem that says rational functions are continuous everywhere, wherever it's defined. Okay, so it's everywhere except at the points where it's not defined. And of course, where is this not defined? Well, we already established that, right? This picture shows you where it's not defined. So it's continuous everywhere, all of these points here, except on the points on the red lines, right? So it is continuous wherever it's defined, because g is a rational function, which is a polynomial over a polynomial in x and y. And so the answer, it's continuous at every point where y is not equal to plus or minus x, which is in every point in the domain, it is continuous. Okay, number 3. Going back to this, number 3 is this function x cubed plus y squared times e to the x, and we are supposed to find the partials. You notice here, all the problems here have to do with linearization and linear approximation and tangent plane. So keep that in mind. All right, so how do you do that? What is linearization? How do you find it? Remember, you use the gradient. All right, so you first find the gradient of this function, which is, of course, the partial with respect to x and the partial with respect to y, and you get this. And since the point that you are to apply this at is at 0, 1. Okay, and by the way, they give you the last coordinate, okay, which is just f of 0, 1. Okay, and simply plugging in 0 here for x and the 1 for y will give you 1 as the function value at 0, 1. Right, so 0, 1, 1 is definitely a point on the graph. It's good to know, even though that is already in the problem, right? So to find, well, first you find the gradient, okay? So you found the gradient. You also found, or you are to find fxx and fyy. What are those? Well, this is the derivative of this fx with respect to x again. And you can clearly see it's 6x plus y squared times e to the x. Remember, the e to the x doesn't change when you take the derivative. 5,000 times, it doesn't change. F sub x, now fyy is the derivative of this with respect to y. So you just lose that y in the middle and it becomes 2 times e to the x. The mixed partials are fxy, which is to take the derivative of this with respect to y. And of course, the first part disappears. The second part becomes 2y times e to the x. For this one, you take the partial fy and take the partial of that with respect to x. And of course, that doesn't change. And notice here, fx, these two are the same as we expect, okay? Because that's what the theorem tells us for most of the functions, nice functions, functions where the partials are the continuous functions. All right, and then for part B, find the equation of the plane tangent. Okay, so to find the plane, remember you have this kind of a surface, and that is the graph of this function. It's got definite curves, and you're supposed to find this tangent plane, right? So what is the tangent plane? You have to find the normal vector first, and the normal vector is found, remember, is fx, fy, -1. That's what you have to remember. So you take the gradient, which is at this point, 0, 1, the gradient is 1, 2, okay? This is easy to calculate. And so the normal vector, or a normal vector to this, this tangent plane and to the graph of the function f, turns out to be 1, 2, and -1, okay? And so that is your normal vector. And once you have a normal vector and a point, this point happens to be 0, 1, 1, which is right here, 0, 1, 1, right? Then you can just plug in these numbers into the formula for a plane. So the numbers 1, 2, -1 happen, 1, 2, -1 happen here, 1, 2, -1, right? These are the coefficients. And these numbers happen at, right, at these spaces, and so you will get your answer, which is this. Now, I would appreciate you making one side equal to 0 and simplify it, because then, you know, I will not have to find all kinds of variations of the right answer. This is sort of a unique, if the coefficients are sort of in the lowest terms, and if the leading number is positive number and one side is equal to 0, right? Although there are many other ways to describe the same plane. All right, part C, find the directional derivative at 0, 1. So I'm still talking about this point. So the question is, what is the rate of change if you are to go from this point in the direction of the given vector v, which is 4, -3. Now, v is 4, -3, but you know, of course, that you have to make sure that you normalize it first, okay? So if v is 4, -3, you normalize it, and the length of vector v is, of course, 5 by the Pythagorean triple. And so if you normalize this, let's call the normalization, or the normalized vector u is 4 over 5, -3 over 5. All right, and all you have to do is take the dot product of the gradient at that point with this normalized vector, and you will not, listen, you will not get a vector, right? Because when you take the dot product, you will get a number, a constant. And in this case, it's -2 over 5. And so that means the rate of change is negative at this point, and this is the correct answer. All right, part D, the linearization. Let's use the linearization, and we are to approximate this function at the point near 1, 0. So the given point is 0.01, 0.98. Okay, now remember the given point was 0, 1, right? And so the linear approximation is going to be taken, of course, at 0.01. So that means dx is at 0.01. And dy, this number is compared to 1, well, it's -0.02. Okay, So these you can use if you like. I have done this in two different ways, and here's what I'm showing you two different ways. The first is to find the linearization, okay? Now, the linearization or the linear approximation, it's basically the same equation as this. If you solve this, if you solve the equation of the tangent plane for z, okay, you basically move this on the other side, you get x plus 2y minus 1, right? And remember, this will be a linear function. There will be no squares, no cubes, no square roots, or no sine and cosine, because it is a linear function. I mean, after all, it's a plane, right? It's a flat plane. And so this is going to just give you the linearization. You can just plug in numbers, 0.01 for x and 0.98 for y, and you will get your answer here, all right? I mean, really, what's LF? The linearization of F is basically this plane, right? And what we are saying is very close to this point, 0, 1, if you change the X and Y just slightly a little bit, then the real value of F is not going to be very different from this point on the plane, all right, tangent plane. That's what this is saying. Or you can use what we call the total differential. Remember what a total differential is? df is fx times dx plus fy times dy. Of course, fx and fy are evaluated at this point, which was 0, 1. So of course, fx is 1, fy is 2, and then you calculated these dx and dy, you plug in these things in here, and that is the total differential, which approximates the real difference in the value of the function at 0, 1 and at 0.01 comma 0.98. So this is approximately equal to the value of the function at the base point, 0, 1, plus this total differential, which turns out to be negative 0.03 in this situation. And so you also get the same answer as the first time. You can do either of these methods if you are asked about a linear approximation. All right, going back there, number 4, you are to use appropriate chain rules to answer each question, right? So I have given you zxy for the first one and then zxy for the second one, so that we don't have to keep looking at these two different documents. Here I've written down those formulas given in the problem. All right, so part A, we are to use an appropriate chain rule to find dz dt, all right? So in this case, you are given x and y, both in terms of t only, right? So this is not the partial of z with respect to t. You get that? It's not a partial because z only has one bottom line parameter, which is t, right? So it's dz dt is equal to, and so this is what we call case number 1 of the chain rules. We have many chain rules now, infinitely many in case you didn't know. But anyway, case number 1. And so you write down that appropriate chain rule. I highly recommend you actually do write this thing down, right? And then just plug in the partials. The partial of z with respect to x is using the chain rule. Cosine, of course, becomes negative sign. Inside stays the same, and then you multiply that by 2, right? So what I have drawn here in green is also green. So you see the color coordination here, right? So here, this is, green portion is still represented by green on the next line. The orange portion is represented by orange line in the second orange part in the second line, and so on. Anyway, so if you find your partial of z with respect to x and with respect to y, which is an orange, and then dx dt and dy dt, you get this line here. Then you just simplify. You see negative 2 times 2, that's negative 4, and then e to the 2 square is e to the 2t is there, and then you have the sign of this quantity, and then you have negative 3, 2, that's negative 6, and then you have the t, and then sign of this, right? Now, traditionally, you are asked to, and I would expect you to do this also, to just not use anything else except t and try to simplify it. And that's why I didn't want to leave x and y in my solution, right? So replace x with e to the 2t, y with t squared in your final answer, right? And then part B, you have to find the partial of z with respect to s. Notice here, this time you have two parameters, okay, for x and y. So this is indeed the partial derivative of z with respect to s that you are looking for. And so this is case number 2 in that chain rules section. All right, and so with the partial of z with respect to x is, of course, 2 times 2x times y, that's 4xy. And then partial of x with respect to s is, of course, 2, and so on. You plug in and you find all these 4 components and write them down. Try to simplify and rewrite x in terms of t and s. Rewrite y in terms of t and s in both of these terms. And you do not have to simplify any more than this, okay? As long as I see that you have correctly, or you demonstrate that you correctly place, use the appropriate chain rule, I would be okay. All right, going on to number 5. Find the directional derivative of this function in the direction of v. This is already normalized. I hope you can see that. I mean, if you calculate the length of v, it's 1. So you don't have to normalize that anymore. And that means you just take the partial, or the partials, so you can construct the gradient, and that's how you do that. Number 6, you take, number 5, going back there. Take the gradient, all right, and you will see, because f is xy plus 2yz minus zx, so the partial with respect to x is y minus z, and with respect to y is this, and with respect to z is this. It's easy. Plug in 1, 0, 2, and you will get, for instance, here, it'll be 0 minus 2, so that's negative 2, and so on. And evaluate your gradient at this point 1, 0, 2, and you dot that with the given vector v. And remember, the answer will not be a vector. It's one number, and this number is negative 8 over the square root of 3. Do you have to rationalize the denominator? No, okay? You can if you like, but it is rather meaningless for a mature student like you. All right, number 6, find the local maxima and minima. All right, so this is, now it's involved, right? These last 3 questions, like I said, will take a lot longer than the space appears in this practice test. Number 6 is find all local maxima, minima, and saddle point. There is no domain given to you, which means the domain is a set of all, the plane, or the set of all the points, x, y. And so it really comes down to finding critical points, right? So take the partials, number 6, take the partials, fx and fy, all right? And it's going, and of course you set them equal to 0, set each of them equal to 0, and then you solve this system of equations, quote unquote, simultaneously. But I guarantee you will not do this simultaneously, not exactly at the same time, because we can't, right? So you do solve this sequentially, like we do everything. Number 1 is really hard to solve. In fact, it's impossible to solve just number 1 by itself. But look at number 2, right? E to the negative x, that never becomes 0. So that means this has to be equal to 0. That means y has to be equal to 0, right? Now, because y has to be equal to 0, this is 0, this is 0. That means 2x has to be 0. Wow, that was easy, right? 0, 0 is the only point that would satisfy both 1 and equation 1 and 2. And so this is the critical point, all right? Good. All right, so if you had like 15 critical points, then you have to check, each one of them to see if that's a local maximum or minimum or saddle point. You don't have to do that that many. In fact, you just have to check 1. But in order to check to see if this is a maximum or minimum or saddle point, you have to find your Hessian, right? The discriminant or the determinant. sorry, not discriminant, the determinant. So, so that means you have to find fxx, fxy, fyy. Remember that the determinant is, or the Hessian is fxx, fyy minus fxy square, right? And so that would be 2, and then 2 minus 0 square and 4. If this were negative, then you would have a saddle point. But since it's positive, it is one of those, positively curved surface, either a maximum or minimum. We don't know yet, but then you look at the sign of that, fxx, which is always, by the way, going to be the same as the sign of fyy. They're both positive. Since it's positive, you know it has to be a local minimum. Right? Is there any local maximum? Is there any saddle point? And the answer, is absolutely not, because if there were a local maximum or saddle point, then you would see another critical point. Those things only happen at critical points, and you know that there's only one critical point, which happens to be a point of a local minimum. So you can guarantee, bet your money on the fact that there is no local maximum or saddle point. All right, 2 more problems here. Number 7, find the absolute maximum and minimum. And you say, oh, yikes. All right, because this is the kind of problem that takes the longest, right? And then they give you a bounded, the bounds, square region. And you say, yikes again, because square means you have 4 edges, right? And you have to check all 4 edges. All right, so I'm not going to go into all the details, but for number 7, you are given this function, a rather easy function, right? And then fx and fy would give you critical points. Set them equal to 0, and the second one tells you x has to be 1. Plug that into equation 1, and you'll find that y2 has to be 1. That means 1, 1 is the only critical point, right here. And you draw, I would highly recommend you sketch your domain. In this case, the domain is the 2 by 2 matrix, 2 by 2 square region shown here. Okay. Now you have some work to do. You can label these sides S1, S2, S3, S4, and for each one you check for any possible maximum or minimum points. The points I called the usual suspects. Remember? So in S1, x is always 0. So, if x is equal to 0, this is gone, right? So then this will be 3x, in fact, this is gone too. So it's negative y. This is the only thing. I should not keep these red lines here. Okay, so, and so if you take the derivative of this with respect to y, of course, it's never equal to 0. So that means what I'm showing here is that nothing interesting is happening on this line. Nothing unusual. There is no local maximum or minimum in the middle of this edge. Okay, that's what it means, no critical points. S2 is where y is equal to 2, right? So on this line, y is equal to 2. And so plug in 2 for here, and then you will be able to come up with this equation. Take the derivative of that with respect to x, and there is an interesting point, a usual suspect, where x is equal to 1/2. So this is this point that I used my black ink to show, right? Something is happening here, something may be happening. And later we'll find out that it may be a local maximum or minimum when you restrict the function f just to that side S2, okay? So let's go ahead and evaluate the function at that point here, and you get negative 9/4. Okay, this is all you have to do is to plug that number, number 1/2 for x and 2 for y. Now S3, S4, you do the same kind of thing. S3 is the edge where the point, every single point x is equal to 2, and then you find your equation f of y. Take the derivative, set that equal to 0. And you find out it's never 0. So there is no unusual or no strange points on this. But on S4, again, you find when y is equal to 0, you have this function, which becomes, the derivative becomes 0 at 3/2. Okay, so this, again, this particular point that I am going to highlight here with black point here, that point is, so this is 1/2, this is 3/2. So these are usual suspects, all right? And so you evaluate the point, you evaluate the function at that point, all right? And then do not forget the corners. You have 4 corners, 0, 0, 0, 2, 2, 2, and 2, 0. And you do not have to apply, again, let me say this again, do not apply the second derivative test for absolute maxima and minima, because locally, I don't care if it's a maximum or minimum or saddle point. All you care about in this case is, because you're looking for absolute maxima and minima, all you care about is the value of the function at each of these usual suspects, the corners and these points here, and the point right in the middle, right? So evaluate the function at 0, 0, 0, 2, 2, 2, 2, 0, the 4 corners, and at the only critical point we found right in the middle of it, and at these usual suspects. So in this case, you have 1, 2, 3, 4, 5, 6, 7. 7 points to check, all right? And the maximum value among those 7 would be the absolute maximum. And the minimum value would be the minimum, the absolute minimum. All right, so you have 0, -2, 0, -2, -2, -9/4. -9/4 is approximately -2.2. Well, it's -2.25. So these are the lowest. And so that's the absolute minimum occurring at these 2 points, 1/2, 2, and 3/2, 0. The absolute maximum is 0, right? Because among these 7 values, or the values at these 7 points, 0 is the highest. So the absolute maximum is 0, right? Now, if somebody comes to you after your analysis, if somebody comes up and says, hey, look, you see this point here? I have found this very strange point where the value is actually positive. You can say, no way, that is wrong. And you can say that with confidence because you did find the absolute maximum using, the theorems about these functions. All right, that would lead us to the final question. Find the maximum product of 3 positive numbers, x, y, z, whose sum is 60. Very simply stated, one line, but it is a rather complicated, maybe, an optimization problem, right? You're trying to maximize the product xyz under the constraint that the sum x plus y plus z is equal to 60. All right, so this is the way we state this. We want xyz all positive so that, so as to maximize xyz, and under the constraint that x plus y plus z is equal to 60. I will show you 2 different ways of solving this, one according to section 7, one according to section 8. All right, so first you use the constraint. Let's solve this for z. Okay, so z is, here, let's use red here. Z is 60 minus x minus y. Plug that into the equation p, which we are trying to maximize. We write p as a function of x and y, 2 parameters or 2 independent variables, right? And then you take the partials, set each of them equal to 0. So this is equal to 0. This is equal to 0. Now, these are not linear, but remember x, y, z are all positive. In particular, they are not 0. So you can divide this by y and this by x, and they will give you these 2 equations. Now you have a system of 2 linear equations. All right, you can call them y 1 and 2. You will see that x has to be 20, and that means y has to be 20, and that means z has to be 20. There it is. That's the answer. Okay. And by the way, you know that the domain, there's no domain here, but well, I mean, x, y, z have to be positive. But if they have to add up to 60, the highest each one can be is 60. Okay. In fact, x can't be bigger than 60, and the x plus y can't be bigger than 60. So the implicit domain is actually this triangular region, not even the points on, well, the points on the line are not allowed because x, y, z cannot be equal to 0. And you know there has to be a maximum point because when you multiply 3 numbers, and if the boundaries will give you the 0 product, then somehow there has to be a highest point. All right, and so this is the answer, 20, 20, 20. The other way to do that is to use the method you learned in 4.8, Lagrange multipliers. You only had a couple of, maybe 3 problems in your homework, but it is cool, right? So you take f, you take g, and then you're trying to maximize f under the constraint of g. And so you take the gradient of each, set the gradient of f equal to lambda times the gradient of g. And the gradient of g in this case is really easy. It's 1, 1, 1. Right? So this side will be lambda, lambda, lambda. And because all of these are non-zero numbers, you divide, well, you know, the first 2 will give you yz is equal to xz, where z is positive. So that tells you y has to be equal to x. And similarly, if you combine 2 and 3, you will see that z has to be equal to y. Basically, this is saying all of these are the same number, x, y, and z. And because the sum is 60, then each of them has to be 20. Okay. Cool. Okay, so that's it. Just make sure that you know how to do these problems. This is a good summary of chapter 4. And let's see, is there anything else that you need to know? If you do, you feel free to contact me. All right, so I hope that you have been diligent in preparing for this test all throughout chapter 4. And as I said, this is the last part of this course where we directly work with derivatives. And so I hope you do well, and let me know if you have any questions. All right, I hope you'll have a great rest of the day, and I'll see you later. Bye.